Welcome to the end of cycle 10. Just like last week, I have modest goals for us. Most of the propositions in this section were fairly straightforward as before, so the ones that we're going to look at together are going to be problem G. We're also going to look at proposition 35 and problems H and I. So we're going to begin with problem G. Now, problem G is an easy one to overcomplicate. It's actually a very simple proposition to solve, or I should say that the problem that it presents is a very easy one to solve. But if you're not paying attention, it can be easy to make it way too difficult on yourself. So this one's pretty much an exercise in, in seeing what the simplest solution really is. And so we're given here the question, which is what is the sum of the angles in any given parallelogram? And here I've drawn out a parallelogram for us, A, B, C, and D. And to answer the question of the sum of the angles, it really is as simple as drawing a line. So I'm going to join B and D. You could join A and C, of course. It doesn't really matter which ones you join, but I'll just join D and B. And so then the rest of my proof will go like this. So I begin then, let ABCD be a parallelogram and let DB be joined. That's what I've got so far. Next, all we have to do is talk about the two triangles that we have. Because we have triangle ABD and triangle BCD. So let's just make that explicit. So we have triangle ABD. So triangle ABD contains two right angles. How do we know that? Well, we know this, of course, from proposition 32. And similarly, triangle BCD contains two right angles, again from proposition 32. Then all we have to do is put the triangles together. But ABCD is made up of triangles ABD and BCD, each of which contain two right angles. Therefore, ABCD contains four right angles. And that's really all that there is to it. It doesn't need to be any more complicated than that. It really is as simple as dividing this parallelogram into two triangles, because we know how many angles are in a triangle, and by dividing this up into two triangles, we can very simply say how many angles are in the entire thing altogether. So this brings us now to proposition 35. Which says parallelograms which are on the same base and in the same parallels are equal to one another. Now, I have always found this to be one of the more enjoyable propositions in this set to work through. Part of the reason is that the conclusion is rather unexpected, I think, and the other one is that the way that the areas are compared, you have the subtraction of equal areas, addition of equal areas. All of those moves, I think, are really fun moves to follow around in the argument. So let's go ahead and look at what Euclid does. Also, you'll notice that I drew my figure a little bit differently than the one in your book. I like to exaggerate the figure more than the figure that appears in your book, because the figure in your book has parallelograms that are pretty similar to each other in terms of shape and angles. They're not identical, but they are fairly similar. Mine, however, you can see is more exaggerated. The differences between these two parallelograms are more exaggerated. And that, I think, makes the argument a little bit more interesting, just because, again, the illusion that the parallelograms are different sizes is really emphasized by making the parallelograms look like very different shapes. So Euclid begins saying, let ABCD, that's this parallelogram here, be a parallelogram on base BC, and we have this other parallelogram here, BEFC, or as Euclid calls it, EBCF, and they are in the same parallels AF, that's this top line there, of course, and the base BC. So they're in the same parallels, right? And the claim is that these two parallelograms will also then be equal. So the argument begins that because ABCD is a parallelogram, AD is going to be equal to BC, because according to proposition 34, the opposite sides in a parallelogram are equal. For the same reason, in our other parallelogram, EFCB, BC is going to be equal to EF. Now, because EF is equal to BC and AD is also equal to BC, then by common notion 1, things which are equal to a third thing are equal to each other, therefore AD is equal to EF. Now, also appealing to another common notion, this time common notion 2, we can say that AE, so length AE, is equal to DF, because we've taken two equal segments here, and we've added a third one to each. So adding DE to AD makes AE, and that, of course, is going to be the same length by common notion 2 as DF, because we have EF, which is equal to AD, and we're adding that same length DE to it. So AE is equal to DF. Now Euclid goes back to proposition 34 at this point to prove that AB is equal to DC, because, of course, this is a parallelogram and opposite sides of parallelograms are equal, so AB is going to be equal to DC by proposition 34. Now he could go on to do the same thing for sides BE and CF, again appealing to proposition 34, but he decides to mix it up a little bit and actually argue and prove that the angle here, EAB, is equal to angle FDC. And of course what he's trying to do is he's trying to prove that these triangles are equal, and the triangles are triangles ABE and DCF. Those are the two triangles he's trying to prove equal. And as I said a minute ago, he could have proven that BE and CF are equal, again by proposition 34, and then he could have used proposition 8 to prove that the triangles are equal. But instead of doing that, he's taking this route, saying the angle here at A is equal to the angle at D. Why? Because this is a parallelogram, and this is the exterior angle of a line that falls on two parallel lines. And so by proposition 29, this exterior angle is equal to the interior angle. But having said that, we now have a side, that's EA, an angle, and a side AB equal to a side, that's FD, an angle, D, and side DC, which makes our triangles equal. So we have triangles EAB equal to triangle FDC. So those two triangles are equal. Next, now we have those two triangles equal, what we're going to do is we are going to subtract this common area DGE from each. So if we imagine subtracting that area, what we're left with then is this space here, the space in that section, and then of course the space over here. And of course these two spaces are going to be equal because we've subtracted this bit from both triangles. The triangles were equal, we subtracted this bit which was in both triangles, and so the remainder then is going to be equal. So those two shaded areas are equal. But then the last step is a very simple one. All we have to do then is add GBC to this other area, ABGD, that we had left over. So if we add it, then we complete our original parallelogram. And if we add this same area here, GBC, to our other remaining area, EGCF, again, we complete the second parallelogram, having gotten rid of this section up here. And what we find is, because this bit that I shaded a second ago is equal to this bit over here that I shaded a second ago, and because we added the same area to each, then the holes, that is parallelogram ABCD and EBCF, that parallelogram, the holes are going to be equal as well. And that's it. So I think this is an elegant proof and fairly simple, but unless Euclid had actually walked me through this proof, I don't think I would have been able to come up with the proof on my own just from the diagram, which is one of the things that I really like about it. The proof is not immediately obvious to someone who doesn't already know what it is, So now we come to problem H, and I have already sketched out the figure here as you see, and I'm going to walk you through one possible way of proving that parallelogram AHEG is half BCDE. So you'll remember that the givens are these, and I've just written them out. Let ACDF, that's the entire parallelogram here, be a parallelogram having sides AC and FD bisected at points B and E. So these sides have been bisected at points B and E, and then we're going to bisect the lines AF and BE as well. So here we have additionally let BE, which I've already drawn in, and AF be bisected at H and G respectively. So here's the claim. I say that AHEG is half of figure BCDE. So just as I said at the beginning, right? So we're just restating what we're trying to prove. So here comes the main part of the proof. Because AB and FE are equal and parallel, and we know that they're equal and parallel because, well, we know that they're parallel because they're in a parallelogram, and we know that they're equal because we bisected the top and the base of this parallelogram. So we know that those are equal. And we also know, therefore, that AF and BE are also equal and parallel, and this is by proposition 33, which states that if you have two lines which are equal and parallel and they're joined at the extremities by other two lines, that those two lines joining the equal and parallel lines will themselves be equal and parallel. All right, so then we're going to do the same thing next for the other two sides, which are going to be CD and BE. We're going to prove that these are parallel in the same way, equal and parallel. So because BC and ED are equal and parallel, again by proposition 33, CD and BE are also going to be equal and parallel. And this means, of course, that ABEF, which is the parallelogram on this side, is going to be a parallelogram, and as well the parallelogram on this side is also really a parallelogram. And this goes back to the definitions, which I didn't write out, but you could do that. But FE is equal to ED, so that's the next step. So I'm just reminding us that FE is equal to ED. And the reason I'm doing this is to make the argument that because each of these parallelograms, ABEF and BCDE, are in the same parallels and they are on equal bases, that they are equal parallelograms. And that's what we conclude here. And this is by proposition 36. Therefore, ABEF is equal to BCDE. So this parallelogram is equal to this parallelogram by proposition 36 because they're in the same parallels and they're on equal bases. Not the same bases, that's proposition 35, but equal bases, which is proposition 36. So far we began with the knowledge that our big parallelogram here is a parallelogram, and then we had to go through some steps to prove that this is a parallelogram here and that this is a parallelogram here. Next we're going to prove that this figure AHEG is also a parallelogram. And we're going to go through some similar steps. So AHEG is a parallelogram for AG is parallel to HE, and we know this again from a previous step, right? We know that these two lines are parallel. So AG is parallel to HE, and they are equal in length. Why? Because each one of these, G and H, are both bisections of equal lines. And so that means that not only is AG parallel to HE, but they are equal because they're both bisections of equal lines. Okay, and so that means then, again by proposition 33, that AH is going to be equal and parallel to GE because these are straight lines joining equal and parallel straight lines at the extremities, making these, of course, equal and parallel. So that's what we've done so far. Now we have a few other steps that we're going to take just to make these last few steps clear. So we're going to join GH. So now that I've joined GH, I've drawn it out as a dashed line because I don't want it to distract from our figure. So let GH be joined. So AHEG is equal to ABGH. BGH. So what I've done is, this is really a figure of proposition 35, right? So we have ABGH is a parallelogram on base AG, but so is AHEG. That's also a parallelogram on base AG, and they're in the same parallels, which means that this parallelogram here is going to be equal to the parallelogram here, because they're on the same base and in the same parallels. So that means that ABGH is equal in area to AHEG. Now, because, again, AG bisects AF, right? G is the bisecting point. That means that the parallelogram on this side, ABHG, is going to be equal to the parallelogram on this side, GHEF. This should be pretty obvious. And we can prove this by proposition 36, because these are parallelograms on equal bases and in the same parallels. Therefore, the parallelograms on either side of GH are going to be equal. But that means that AHEG is equal to either one of these, so the one up here or the one down here. And the AHEG is therefore half of the whole parallelogram ABEF. That's what we've got written out here. So therefore AHEG is half ABEF. So now comes our very last step. So we already proved earlier up here that ABEF is equal to BCDE. So that means ABEF, the parallelogram here, is equal to the one on the other side, BCDE. So we know that those are equal, and we just proved that AHEG is half of ABEF. But because ABEF is equal to BCDE, that means that the parallelogram here, AHEG, is also half of BCDE. And that's the end of our proof. Now, as I said at the beginning, this is just one possible proof. It's possible to prove this using some different steps, but these are the steps that I've chosen as being perhaps the most straightforward. But if you came up with a different solution, that doesn't necessarily mean that it's wrong. It just means that you'll want to go back and make sure that you've proven the same kinds of things that I've proven. In other words, you'll want to make sure that you haven't taken it for granted that, for instance, BCDE is a parallelogram, or that AHEG is a parallelogram. These are things that need to be proven. You cannot just assume that because they look like parallelograms that they are parallelograms. But as long as you went through the steps to prove that these are in fact parallelograms, then your proof is likely okay. You just want to make sure, again, that you haven't assumed things which need to be proven. But there are other steps we could have taken, and we could have proven that these were parallelograms slightly differently as well. We could have, for instance, divided them up using triangles and gone from the triangle to talk about the angles, etc. We could have taken a slightly different approach there, but the approach I took, I think, is probably the most efficient. Well, I hope that that's helpful then in helping you think about problem H. All right, so now we come to our last problem of the day, which is problem I. Now this one's a little bit tricky because we haven't talked about proportionality or anything of that sort, but I hope that the principles here were simple enough to where you were able to put together some kind of an argument to prove what we're trying to prove. And that is, of course, that ABCD is 6 times larger than triangle EGF. That's what we're trying to prove. So we begin from the knowledge that ABCD is a parallelogram, so the whole thing here is a parallelogram, and that DE is equal to EF, and that EF is equal to FC. And then the claim is that with this information, we should be able to say that ABCD, that's the whole parallelogram, is 6 times larger than the triangle EGF. That's what we're trying to prove. So how do we go about doing that? Well, and again, my proof here is pretty simple. I think this is probably the most efficient way to do it. And so if yours was more involved, that's perfectly fine. But I've tried to do this in the simplest possible way. So let EH, so EH be drawn. So we're drawing EH parallel to AD, and I've drawn JF parallel to BC, and of course, because the whole is a parallelogram, BC is also parallel to AD. And so then we conclude that AHED, that's this parallelogram, is a parallelogram, and that this is also a parallelogram, and that this figure is also a parallelogram. How do we know this? Well, because each opposite side is parallel. So this side's parallel to this side's parallel to this side's parallel to this side, and we could go through this in more detail if we wanted to, using the common notions just to prove that each opposite side is parallel to the other. I've just sort of left it as this because I think this is sufficient. Okay, next we're going to prove that AHED is equal to HJFE. So AHED is this parallelogram here, and we're going to prove that it's equal to the middle parallelogram. How do we know that they're equal? Well, because they're on equal bases. Remember, the equality of the bases is part of the given. And they're in the same parallels, obviously, and they're on equal bases. Therefore, by proposition 36, these parallelograms are equal. But this base is equal to the others, and this parallelogram is also in the same parallels, and so this parallelogram here also has to be equal to this parallelogram. And then we could apply 36 again and say, well, this one is also equal because they're on equal bases. But here I just use the common notion to say things which are equal to the same thing are equal to each other. So because we know this parallelogram is equal to this parallelogram, and we know that this parallelogram is equal to this parallelogram, then these two on the ends must be equal to each other as well. So a couple different ways to prove that. Next, we're going to say that AHED, HJFE, and JBCF, that's each of these three parallelograms, are together equal to the whole parallelogram. That's not something we can assume. We have to prove it. Or at least we have to point it out, right? That these really are, these parallelograms together, if we add them all up, we get the whole parallelogram. That should be pretty obvious, but we need to say it. So add these three parallelograms up, we get the whole parallelogram, and each one of them is a third of the whole. Now this, I didn't write out the reasoning behind this, but I hope it's pretty obvious, right? We know that because this is equal to this and this is equal to this, so each one of these three parallelograms is equal. There are three of them in the whole. That means that each one is a third of the whole. Euclid does this kind of thing pretty frequently, by the way. He's not cheating by leaving out some of these other steps. He just assumes that the reader is going to be clever enough to figure out what he's talking about, and that's what I've done here, right? I haven't explained, well, because these are three, there are three of them in the whole, therefore each one's equal to a third. I've just said, well, because these are equal to this one, each one's a third. I left that intermediate reasoning to you. And that's okay to do, as long as it really is this obvious. If it's something that needs to be proven in detail, you can't do that. But if it's something which just looking at the figure should tell you, because it's really basic arithmetic or something, then that's okay. So next we go on to talk about the triangle. EFG is half of HJFE. So we know that this triangle is half of the parallelogram that it shares the base with. How do we know this? Well, we know this by proposition 41. And we remember that this parallelogram is 1/3 of the whole parallelogram. Now, if we take a half of a third, right, then we end up with a sixth. That's what I've said. So if we take this third and we divide it in half, we end up with a sixth. And so the triangle there is equal to 1/6 the area of the whole figure. And that's how we go about proving that. And again, just like the last one, your proof doesn't have to look exactly like this. You just want to make sure that you prove the same kinds of things. For instance, if you had divided this up into triangles rather than parallelograms like I did, that's okay. I mean, the triangles work just as well. It's just going to involve you in a couple extra steps. And it's likely that any other solution would involve you in a few other steps as well. But the point is, as long as you have something similar to this and you go about proving the same kinds of things, your proof should be fine. And that's all that we're going to do today for Cycle 10. So I hope that this was helpful, again, as always, and we will pick back up next week with the end of Cycle 11.